Characteristic impedance. Do you remember this characteristic impedance? Yeah. And did I do power transform with the transfer in one direction? I did. Okay. I got all that down. Okay, so before I get to terminated lines, does anybody have any questions about the homework? Right now?
I think it was just even one. It was just one with a bunch of things for one.
You gave us some reading.
Some reading.
Does everybody understand that from?
Mm-hmm.
All right. So I want to do one more example. So, think about, remember you were introduced to a lot of concepts. There was gamma, right? Gamma was equal to the square root of j omega u. Pardon me. I'm doing this one time. Let me get it the other way. Gamma is actually equal to, this is per meter resistance, R plus J omega L, and G plus J omega C is equal to alpha plus J beta. Then the characteristic impedance for positive going waves, E0 plus over I0 plus, is equal to the square root of R plus J omega L over G plus J omega C. And that can be complex. We talked about that. We talked about phase velocity, right? Omega over beta. We talked about wavelength, which is 2 pi over beta. And we talked about a few other things. Y'all remember this class? So, in general, if I asked you for, I'm going to give you just a for instance. Actually, back here. I'll do power transfer. Should we go? Actually, this book doesn't have this. All right, we'll do 2.6. I don't know if that is the problem I gave you or not, but for problem 2.6, we'll just do this. It says we're at a frequency of 100 megahertz. And we have Z naught given as 18.6 minus J 0.253.
Yeah, this is the same problem.
All right, we did that?
This is the homework.
Okay. And you did that? You had no problem with it? Okay. Then I won't even bother with that. I'll get right into what I was going to talk about, because he does not have many problems related to just R, L, C, and G. But I'll erase that and get into the power flow. So I talked about power flow in one direction, and if you have a transmission line with the characteristic impedance of Z naught, and we're talking about now power flow, average power flow down the transmission line. We want to know what it is. I did that, and I said, well, if it's moving in the positive Z direction, we'll call this the Z axis. So we're talking about something that's moving in a positive Z direction, the entire wave. And remember, V of Z was equal to some V0, e to the minus alpha Z, e to the minus J, beta Z, and I Z is equal to V0 plus over Z naught, and times e to the minus alpha Z, e to the minus J, beta Z. Do y'all remember this? I'm just restating what I said before. If you have this, and you go ahead and get the average power flow, it's equal to, this is again in the phasor domain, it's the average power flow, times the real part of V times I conjugated. We did this and we mentioned that this V here, you can just put down there, for I conjugated, well, Z naught has a magnitude and a phase angle. So the phase angle would appear as minus J theta Z here because when it's downstairs, it would be plus J theta Z. If you take it to the numerator, it would be minus J theta Z. And then when you conjugate this, the two complex components they change sign, become positive. But at the end of the day, the average power flowing down here is going to be 1/2 magnitude of V naught plus squared over magnitude of Z naught. Then it's going to be e to the minus 2 alpha Z, and it'll be cosine of theta Z. And this will be in watts. That's the general form of the power flowing. So if you take a look at this for a second, you can see one thing. Everything that I circle here has a single constant value. Do you all see that? Yeah.
What page is this on in the textbook? 45.
Thank you. All right, but you all take one look at that and you can see that all of those terms are single constant value. And for a wave propagating in a positive Z direction, what we can say, and I'll just draw this, if we have a transmission line as such here, then we'll call this Z equals 0. And this will be positive Z this way. Then the power flowing at Z equals 0, this would be P of Z at any point down the line. It would be average power, is equal to some P0 e to the minus 2 alpha Z. And P0 in this case is just going to be 1/2 magnitude of V naught squared, magnitude of Z naught times the cosine of the phase angle. Do you all see this, class? I'm trying to make it simple. Everybody with me? And you can see as it propagates down the line, it's decaying at this rate, e to the minus 2 alpha Z, twice as fast as the E field or the current would decay, voltage or current would decay down the line. Now, one of the things that they talk about often is dB, decibels. You all heard of decibels?
Yes.
All right, so when we talk about decibels in general, if you're talking about voltage or current, write this down if you don't know it. And you want the decibel value. If you want V in dB or decibels, that's 20 times the log of V, period. And I'll give you an example of this. So you use a 20 there. If you want the current in a decibel value, it would be 20 times the log of the current. This would be magnitude, log of the magnitude of the current. Now this is just generally true for voltage or current. But when you talk about power, then you would say the power in dB, this is a general form, is 10 times the log of the power that's actually going to be in watts, or the linear value. There's a 10 there, not a 20. You all remember this? And these are log-based 10s. How many have seen this before? Where did you see it? In what class? What's that? Signals and systems? Good. In your laboratory work, you may have seen something like this. Now I'm going to show you the standard units that are used if they want exact measure. And I'm going to do it over here. Yeah.
What's the subscript on that field?
Average, just average value. It's not instantaneous, it's average. So if we come over here, let me get this out. And now, these are standard units that are used for power and voltage and current. Usually they talk about voltage in dB microvolts, dB microvolts. And that's 20 times the log of the voltage in volts divided by 10 to the minus 6. I say it's normalized by the value of 1 microvolt. Do y'all follow me? I'm going to put these down. We'll do some examples. Then I'll get into the actual alpha and dB per meter versus alpha and nature. If we talk about a current in dB microamps, it's 20 times the log of the current. By the way, that's magnitude of current and magnitude of voltage over 10 to the minus 6. That's dB microamps. They're very common. These units are standard. When I teach EMC and in radar, we use these commonly. And then with power, power is in dBm. That's milliwatts. And it's 10 times the log of the power, really power over 10 to the minus third watts. Now, these are, have you heard of dBm? If you have phones, you can look up, I believe, your cell phone, the nearest tower's power being received at your phone in dBm. If you have one, you can try it. When I do EMC and radar, I have people do this because it's extremely low. Let's just talk about a few of these things. So with voltage, if we're talking about dB microvolts, and I have a voltage of 10 millivolts, and I want to know what that is in dB microvolts, it's equal to what? 20 times the log of the voltage. 10 millivolts is what? 10 to the minus 2 volts. Did you agree with that, everyone? And then you divide that by micro, which is 10 to the minus 6. So that's 20 times the log of, and this is going to be what? 10 to the 4th, right? So 10 times log of 10 to the 4th is what? 4 times 20 is 80, and this would be dB microvolts. Do y'all follow me on this? Now let's go the other direction and keep going. That's 10 millivolts. What if I have, say, 1 nanovolt? That's almost impossible to measure. 1 or 10 to the minus 9 volts. Then what do you get from now VdB microvolts is equal to 20 times the log of magnitude 10 to the minus 9th over 10 to the minus 6. That's 10 to the minus 3. Or this is minus 60 dB microvolts. Do y'all follow me? Now the reason we use dB microvolts and not volts is because when you have orders and orders of magnitude, like 6, 10 orders of magnitude of difference in voltage is possible, and happens a lot when you have signal and noise, and you get just noise signal. Then they use this because it compresses the actual domain down to roughly plus or, it's really going to be about 100 dB either way. If you look at this, that's 60 dB, that's 80 dB. We're getting close to the limits of about 100 dB positive and 100 dB negative. That's 200 units of dB microvolts. That's going to span 10, 12 orders of magnitude of actual values. Do y'all follow me? So that's why that's used. What about power over here? If we do power in dB microvolts, or I mean power in dBm, think about that for a second. Come over here. And this is real common units too. If you're used to just volts, millivolts, microvolts, stuff like that, I don't think you use this commonly in your laboratory work yet, but you will probably in time. So what if we have a power equal to 10 watts? What's that power in dB milliwatts, dBm? It's 10 times the log of log of magnitude of 10 over 10 to the minus third. That's 10 to the 4th. What's the log of 10 to the 4th? Log base 10? 4, right? 4 times 10 is 40. So it's 40 dBm watts. And that would be for 10 watts. Now, what happens if I have a power of, say, 1 microwatt, or 10 to the minus 6 watts? Now what's the power in dBm? 10 times the log of magnitude of 10 to the minus 6 over 10 to the minus third, right? That's 10 to the third, 10 to the minus third, so that's going to be minus 30 dBm. And again, I'm going over how many? 7 orders of magnitude there. Y'all agree with that? And you can see I go from minus 30 to 40 dBm, which is a very compressed range, and that's the reason we use dB. dBm for power, dB micro for voltage, dB microvolts or microamps, and that's typical. In EMC and the work, when you get into RF amplifier design, and things like that, you'll be using these type of units continuously. Dr. Wentworth's book does one thing. He shows you something where we talk about the attenuation in dB per foot, or dB per meter, that's, and it's decibels per meter, and then he talks about it, the relationship to Napier's per meter in terms of the standard form of alpha, and I'm going to do it over here. So, and I think you'll understand this way of doing it. Let me do it right here. So if I have a transmission line as such, and we can assume this goes on forever and ever, and it's got a characteristic impedance of Z naught. And this is going to be Z equals 0 right here, and the power is transmitted this way. So that's the direction of power flow. I come over here and I'm going to say that the actual power coming down this line, P of Z, its average power, is going to be some P0 e to the minus 2 alpha Z. Now y'all follow me? That's just standard. So it's something that's traveling in that direction, assume the line's infinite. So how much power loss occurs over a 1 meter section? Now I want you to just take a look at this. If I have 1 meter section here, what we're going to do is see the power loss in dBm, or sorry, in dB and also in Napier's per meter. So alpha right there has units of Napier's per meter as such, and that's the alpha that comes from that gamma is equal to alpha plus J beta. So if I have P naught entering here, right here, this would be P naught, right? It's 0 because Z is 0. Then 1 meter down the line, if I say this is 1 meter, I would have a power equal to P0 e to the minus 2 alpha. Y'all follow me in that class? So if we take a look and see how many dB of attenuation occurred right here, I would say the amount of attenuation would be what? Well, this is what comes out, that was what goes in, so we're going to have, if I take this to dB, it's going to be this way. I have P0 goes to 10 times log of P0. Then I have P0 e to the minus 2 alpha times 1 goes to 10 times the log of P0 e to the minus 2 alpha. This is equal to 10 times the log of P0 right there, plus 10 times the log of e to the minus 2 alpha. Remember the log of A times B is log A plus log B. Y'all remember that class? Everybody? Right, now take a look at this. So I started with P0 log of that. I ended up with this. I'll expand this further. This is 10 log of P0 minus, now take a look at this. I got minus 2 alpha. Well, that's anytime I have a log of A to the B, I can just take B out further. So it's minus 20 alpha right there times log, and this is going to be a log base 10 of E here, would be the amount of power loss in dB. I started with this, I ended with this, 1 meter down the line. That means per meter, I have minus 20 times alpha, the log of log base 10 of E. And that is actually equal to minus 8.686 alpha. And this would be the attenuation in dB per meter. Now, he'll omit the negative sign in his book. But what it really is saying, if we wanted alpha, or the attenuation in dB per meter, it's 8.686 alpha, where this alpha is in Napiers per meter. Let me tell you where it is in his book so you can look at it. This is page 48. And he just leaves it in terms of a Napier versus a dB, but I like to do it per meter, so 8.68 alpha is equal to alpha in dB per meter. You all see that there on page 48? It's equation 260. Is that every book's here?
Mine comes tomorrow.
Huh?
Mine comes tomorrow.
Do you see it in that?
Yes,
All right, just circle that. I mean, it's not a big hang up. Normally, have you all looked at like coax cables? You know, they'll have a certain attenuation dB per meter. It's real important to understand that. Usually it's dB per hundreds of meters. Typically 4.5 dB per 100 meters, which is roughly, that's not bad, but that's standard like, what is it, RG58 coax. When you have fiber optics, it's almost nothing. It's like maybe 0.1, 0.2 dB per mile. And that's the reason they use that stuff. Almost no attenuation. There's dispersion, but not much attenuation. So that's what alpha means, and we'll do problems so you'll get a better understanding of this. And we will do some problems in a second. I want to get to terminated lines next. This is section 2.4. But I'll use all this at the same time to solve some problems in a second when we do it. And you'll see how all this works. Until you really see it used, it's hard to appreciate a lot of this stuff. I guess it's going to be a rainy weekend. All right, so this is terminated lines, and it's on page 49. Let me go ahead and do this. So what he's going to do is say, when we have a terminated line, we actually put a load on it. So we have a transmission line as such. This transmission line has some characteristic impedance Z0, and now we put a load on it, some Z load. And it's going to develop a voltage here, V load, and there'll be a current here I load as such. Almost always, for simplicity, they're going to assume this occurs at Z equals 0. Z will be in this direction, Z plus. Y'all follow me? They do it just for simplicity. Now on this line, anywhere on this line, you're going to have a voltage, some V of Z, and you're also going to have an I of Z. Y'all with me? Now this is important to appreciate. We're not just going to have current going this way or voltage propagating this way. Because there's a load there, some of it hits and reflects back. We're trying to keep this simple. Y'all with me? So when you write the equation for voltage and currents here on this line, you would get V of Z is equal to some V0 plus e to the minus well, I'll just put minus gamma, because I think he does it this way, z, plus v0 minus e to the plus gamma z, and you'll have I of z equal to v0 plus e to the, over z naught, over z naught, e to the minus gamma z, plus, or minus, pardon me, minus v0 minus over z0. Remember, the ratio of v to I for a negative going wave is actually negative z naught. Y'all remember that? We mentioned this? So that's where this comes in. This z naught is z naught plus, by the way. And it's going to be e to the plus gamma z. Okay, now, that's the ratio of voltage to current. Y'all with me? Now, the ratio of voltage to current anywhere would be considered an impedance, right? If you're right here at the load, the ratio of V at Z equals 0 over I at Z equals 0 would be the load impedance by definition. Do you agree with that? Y'all see that, class? Now, what is that equal to? Well, and in his book, does he, I don't know if he did reflection coefficient. Okay, he's going to do it next. So if you look at this, ZL here would be, just look at this equation, it says Z equal to 0. Now you get V0 plus minus V0 minus over, and this is going to be I0 plus minus, sorry, I better do it that way. I'm going to put in this value. These have V0 and, it has V0 plus and minus and Z0 plus. So this is going to be V0 plus minus V0 minus, but this whole thing, if you divide by Z naught, it's like multiplying by Z naught plus here. Are you with me, class? I'm just trying to rearrange these things. Take a good look and take a moment. Just convince yourself, because Z is equal to 0. This equation on the top simply comes V0 plus V0 minus, and then on the bottom it's just V0 plus over Z naught minus V0 minus over Z naught. The other terms go to 1. Y'all with me? Now, here's the important part. Can y'all see, if we wanted the ratio of V0 minus to V0 plus, we could get it. Take one look at this. I mean, you can do it this way. We could multiply both sides by V0 plus minus V0 minus, and then divide everything. Might as well do it that way just to show you. So I'm going to take this, and first I'm going to say that I'll have ZL on this side. It's going to be times V0 plus minus V0 minus is equal to V0 plus V0 minus times Z naught. Okay, now you all see what I'm doing. Now, we're going to define something that's very important. It's the reflection coefficient. It's how much of this signal that's propagating in a positive direction is going to be reflected back in the negative direction. It's a ratio of voltages. So what we're going to call this is the reflection coefficient at the load. At load, ZL. And this is going to be defined as V0 minus over V0 plus. So it's a ratio of how much is reflected to how much came in for V0. Follow me? All right, so over here, I'm going to take this equation, I'm going to divide both sides by V0 plus. And now I get ZL here. And I get 1 minus, this will become the reflection coefficient at the load, is equal to Z0 plus. And this is going to be 1 plus reflection coefficient at the load. Do y'all follow me? And I'm just using that definition of reflection coefficient. So when I do that and rearrange it, remember I want to get gamma L out of here. On this side I get ZL minus ZL gamma L equal to Z naught plus Z naught gamma L. Y'all follow me? Now I'm going to take this term to this side, so I have ZL minus Z naught is equal to take this term to that side, and then I have gamma L times Z naught plus ZL. Follow me? And again, just rearranging things, because now I'm going to do what I need to do. I'm going to divide both sides by Z naught plus ZL, and this becomes the definition of the reflection coefficient below. It's important you appreciate this. This is ZL minus Z naught over ZL plus Z naught. And this is very, very important that you know. And that's the reflection coefficient below. Now, let me keep going with this. Everybody follow me on this? We're just defining this. And by the way, engineers always take things and lump them down to one parameter when possible if that same thing reappears over and over again. I think everybody does. Mathematicians, physicists, doesn't matter. Makes life simple. So now we rewrite these two equations. So now this V0 or V of Z up here becomes what? V of Z can be written as, well, I can take V0 plus out in front, and it's e to the minus gamma Z plus the reflection coefficient at the low times e to the minus gamma Z, e to the plus gamma Z. That's the first one, V of Z. And I of Z is equal to, now that's still V0 plus over Z0. And then it's going to be e to the minus gamma Z minus gamma L e to the plus gamma Z. And I think he has this in his book. Let me just check. He writes that, that's right, that's right. Oh, this is a little further. This is equation 2.71 in the book. Okay. Everybody with me so far? All right, now we're going to do one thing. I'm going to still stay on topic there. I've got my equations. What we're going to do is find out what the impedance would be anywhere down the line in this direction. So I need to erase this board and keep going. All right. This one's kind of interesting. So now, remember, that's positive Z here. And now what we're going to do is this. We're going to say that if we wanted to know the input impedance right here, call it Zn, as a function of the length of the line, and now I'm going to do this. This is going to be the length of the line. It's strict positive. It's measured from the load to the point where you want the input impedance. Pay attention to this. This is real important. Everybody follow me on this? All right. Now, if I want that, I come back to this. The ratio of voltage to current anywhere on the line is this, isn't it? These two divided by one another, right? So I'm going to say the impedance at any point on the line, put it here, Z in as a function of Z would be equal to this part right here, which is V0 plus, and it's going to be e to the minus gamma Z plus the reflection coefficient at the low times e to the plus gamma Z. And it's over V0 plus over Z0 times e to the minus gamma Z minus the reflection coefficient below times e to the plus gamma Z. Now, I've written it there so you just see it. It's that stuck there. Everybody okay with that? Important you pay attention to this. What do you know about V0 plus? Take one look. What happens to it? Does everybody see it cancels? You got one on top, one on the bottom. Everybody good with that? So if it cancels, by the way, you're recording me. Thank you so much. I appreciate it. If you want to move to the center, you can, but whatever you want.
Plug in. I got the plug in, so I was just gonna leave it here.
All right.
I think I'll probably be alright for this class.
All right. Next
At least
time
I can see
it front.
I can see everything here at least. So
Huh?
I can see it all on my screen pretty
Put
clearly.
over there.
Yeah,
Okay.
at least I think so. I mean,
All right. So anyway, Zn becomes what? As a function of Z, it becomes simply, look at that, Z naught comes upstairs, right? And then you have e to the minus gamma Z plus the reflection coefficient below times e to the plus gamma Z over e to the minus gamma Z minus the reflection coefficient below e to the plus gamma Z. Now, I don't know, do y'all remember hyperbolic functions? Remember before you knew, like operations like tangent of something of x, right there was the sine of x over the cosine of x, right? Remember that? All right, well, when you have hyperbolic functions, it's called the sinh of x is equal, well, actually, the tangent x is equal to the sinh of x over the cosinh of x. And I'm not going to spend a lot of time. Do you all remember? Did you have these things, hyperbolic functions at all? In math? Anybody? Didn't they cover this at all?
A little bit.
All right, hyperbolic functions, there's no trick to them. For instance, if you have sinh of x, or better yet, cosh, cosh of x is nothing more than e to the x minus, or plus e to the minus x over 2. What does that look like? Doesn't that look like Euler's identity for sine? Only what? If it was, cosine, if it was cosine, it'd be e to the jx plus e to the minus jx over 2. Remember, do you all remember this? Y'all had Euler's, right? I put Euler's identities up there. That's all this is using hyperbolics instead of e to the j angle or j argument. So what this boils down to, if you talk about lossy lines, and that means alpha greater than or equal to 0, something lossy, then you're going to get the input impedance as a given distance z down the line, and usually they do this. Now remember, z down here would have negative values. Like right here, this input, z would be equal to minus L, because L is the length of the line, but it's less than 0. Do y'all follow me on that? So what they normally do is put z in as a function of L, length, and they'll get rid of the negative sense to that. So that's equal to z naught, the characteristic impedance, and then it's going to be, the way he's going to do it is going to be ZL plus, and this is going to be Z naught times the hyperbolic tangent of gamma L over Z naught plus ZL times the hyperbolic tangent of gamma L. Where this comes from is, if I take this right here, and I go ahead and I can play around and expand this somewhat, I can get hyperbolic tangent values here and here, and then I can rearrange it and get that, but I don't need you to focus on that right now. Just realize this would be for a lossy line. We don't use that almost ever, just at a time. And he has this, I think in his book, it's equation 2.72. The one we use is for the lossless line almost always. Now you can use this, but if you're using this, it means your line's very bad. But anyway, and this is, I'm going to just say this, this is rarely, if ever, used by me personally. So next is the actual one. This is for a lossless line. And you can put low loss, actually. And that means alpha is small. And I'll explain what small means in a second. So that means the input impedance Zn as a function of the length of the line is equal to the characteristic impedance Z0. Then it's times ZL plus, then there's a J Z0 times the tangent of, and this becomes beta L. It's no longer gamma. And this is Z0 plus J ZL times the tangent of beta L here. This is the one we use all the time. And it is on page, it's shown at, in equation 2.73 on page 51. Y'all hear me, class? So, that shows you basically how to get the input impedance for a line. Let's see if he's got one in here. We're going to do drill 2.8, and he refers back to drill 2.7. And matter of fact, we're going to do all of them. Want to read them? Give me 1 second. Let me erase this right here. Start with drill 2.7, and we're going to move on. Give me 1 second so you can see all this in operation. So this is exercise for example 2.7, right?
Yeah.
And what does it say?
A 50 ohm line is terminated in a 150 ohm.
All right, whenever they say a 50 ohm line, it means the characteristic of impedance is 50 ohms. That's all it means. It's terminating to a load of what?
150 ohms.
Okay.
And then it says find A, which is gamma.
Reflection coefficient of the load.
Yeah.
So first thing you want, reflection coefficient of the load. Please pay attention to this. You're going to be asked this on quizzes. It's coming at you from now until the end of the semester, and then you'll get it again in all your advanced, a lot of it in your advanced courses. You take a look at this. Reflection coefficient is always the impedance you're going into. That's ZL for a positive going wave minus the impedance you came from, which is Z0, divided by the sum of the two. Now, if you look at this for a second, and I'll draw the picture. Normally, you're going to have something. You got some load impedance ZL, and you got a length of the line L. You have some Z0. We're going to talk about the input impedance here, and we're talking about reflection coefficient and all that. Reflection coefficient at the load is always the impedance you're going into, which is ZL, minus the impedance you came from over the sum. Some comments about this. What happens if ZL is equal to Z0 to the reflection coefficient? Think about it, just look. Do the math. If ZL is equal to Z0, what is the reflection coefficient?
0.
0. All the power is transmitted, nothing is reflected. This is something you keep in your head. If the impedance here is equal to Z0, nothing is reflected. That's called a match condition. Everything is accepted, nothing is reflected. That's what you strive for when you make any kind of a network where you have an antenna or something with a power supply or a power amplifier. You want everything launched from that antenna. It has to be impedance matched. It's true in general with any circuit. You don't want stuff bouncing back and forth because you can get all sorts of voltage accumulation and then it will cause all sorts of problems. You got that? So anytime you're communicating, that would be ideal. Now what happens if ZL is a short, 0 ohms? What's the value of the reflection coefficient? -1. What happens if ZL is an open circuit or zero or infinite impedance? +1, isn't it? All right, that's the range. It can be from +1 to -1. That's the possible range of the reflection coefficient. It can't be 3.5. It can't be -35. Not for a passive network. Now, an active network is different. These are strictly passive components. You can't get anything more out than you put in. So those are the possible ranges. Now for this one, what is it by looking? Well, the impedance I'm going into is 150, right? I came from 50, and the sum of these two is 200, right? So that's what? 100 over 200, or 1/2, right? That's not good. What else does he ask for in that problem?
The voltage standing wave ratio.
All right, now we didn't cover that yet, but I'm about to, and I'll do it up here. Because this is something you run into all the time. It's called the VSWR or just SWR, standing wave ratio. It's the same for voltage or current. I'll show you what I mean. When you take a look at the voltage equation, you can put your pencils down, just look at it and listen. In general, anywhere on the line you have V of Z equal to some V0 plus, right? And I'm going to do it for lossless. It's the same for lossy. Lossless line, alpha is 0, comma R equals G equals 0. Then it's equal to e to the minus j beta z. Now if it's lossless, that's going to be true. You agree with that, class? Because alpha is 0. And it's going to be plus the reflection coefficient of the load e to the j beta z. Now I want to do this in a rational sense. You take one look at that. If you were plotting that versus z, you basically have v0 here, and you have two vectors. One is actually moving in the counterclockwise direction. This is moving in the clockwise direction. So if this is the real axis, and this is the imaginary axis, and you were to plot v as a function of z, take a look at the first term. Here, it's going to have a magnitude of v naught. It's going to be at some angle, e to the minus j beta z. I'm just going to try to show you this. So this is going to be some v0 plus e to the minus j beta z. It's an angle. You're going to have another one there, rotating in the positive direction. Actually, this should be positive. This should be negative. And I'm going to have v0 minus, this is minus actually, or v0 plus, pardon me. And then it's going to be times the reflection coefficient times e to the j beta z, and it's revolving that way. This one is revolving that way. Can you all see this? I'm just trying to give you an illustration for a given beta z. When beta z is 0, if that's not complex, they're right on this axis. They're superimposed, correct? Now, if it is complex, they'll be skewed. It's different. As this thing revolves, if you looked at the sum of these two, right here, you let it revolve, you'd find the maximum value of that voltage. The max of V of Z, I'm not going to prove this, but it's true, is going to be V0 plus times 1 plus the magnitude of gamma L. And you'll find the minimum possible of V of Z is equal to V0 plus over 1 minus magnitude of gamma L. Now you can kind of see that here. If you go ahead and just take a look at this thing. At 0, assume gamma L was strict real. The greatest possible value would be 1 plus gamma L times V of Z. That'd be a magnitude. You see that on top? Now look at the minimum. That's when they're exactly opposed to each other. It's one minus the other, okay? So it'd be 1 minus gamma L times V0, or the ratio of V max to V min on that line. This is called the voltage standing wave ratio. Typically it's just standing wave ratio. And that is 1 plus the magnitude of gamma L over 1 minus the magnitude of gamma L. Now, for this particular one, what is the voltage standing wave ratio going to be? Just take a look. What is gamma L? So it's 1 plus 1/2 over 1 minus 1/2. Remember, that's a magnitude, right? That's 3/2 over 1/2, or 3. You all see that?
Yeah.
That's very bad. When you get a voltage standing wave ratio, anything greater than about 1.2 in a design, you're not impedance matching. That's what it's telling you. And I want to tell you a personal story that happened. So, 2002, 2004, somewhere in there, I was working for NASA in the summer, and I had to design an antenna. It's for a synthetic aperture radar, but it had basically 3 arms at 120 degrees to each other, and there was going to be 8 antennas on each. And without getting into too much detail, we developed a scaled model of that thing. When we built it, I designed it with another guy named Dan Faircloth, who's one of the heads of Iris now, that company in Huntsville, and we designed it and we sent it off to be built. So it goes, gets built. I wasn't there. So the antenna comes back, and they get shipped to Ball Aerospace for testing. And they do testing on it. So they're trying to get the antenna pattern and everything. Before going, they look at the standing wave ratio. Now, it was designed for 50 ohms. They have a 50 ohm generator, or feeding the antenna with a 50 ohm source. It should be perfectly impedance matched. Standing wave ratio is 0. Should be 1. So he calls me up, this guy from Ball Aerospace, and thank God he was an engineer, not just a technician. He says, we're getting a standing wave ratio of 4. How? It's impossible. I did the design myself. I know this is impossible, something's wrong. I didn't check the design that we paid for. I didn't check when they fabbed it. So he goes, well, with your permission, I'll look into it. I am an engineer. I'm like, okay, go ahead. So he rips the thing off, rips the seal off. There's a big old solder ball right on the antenna. Normally, when coax comes off, you have to take that and solder it to the antenna. Follow me on this? Well, you know what? A solder ball is like your worst curse when it comes to impedances at high frequencies. This is 1.4 gigahertz. A little higher than that, actually, about 1.4, something like that. And he says, listen, I said, you need solder ball, can I take it out? Yeah, get rid of it. So he gets a solder gun, melts it, gets rid of the solder, puts it back together, measures in standing wave ratios like 1.1. Except, whew. Now the guy that built it didn't know a large solder ball could have a problem. But I hope all of you do. Have you been told to use a minimal amount of solder and always have minimal lead links? That's my personal horrific story, because, you know, with the government, they don't pay you unless you have a deliverable that works. So that would have shorted me. I think it would have really shorted me. Anyway, it worked, thank God. But that's a story about standing wave ratio, and how come I'll never forget that. And it had to do with an impedance mismatch. Basically, this and this were both 50 ohms. There was a big old solder ball that put about 70 ohms there, J70 ohms, just enough to destroy everything that I've tried to do. But I'll never forget. I don't know if it was 70. I know it was enough to cause me to have your heart hurt about it. So that's what standing wave ratio is. Now, let's keep going to the next problem that's related to this.
Is drill 2.8?
Yeah.
Okay. Suppose the terminated T line for drill 2.7 is lossless. Find the impedance and for a length of line equal to A gamma over A.
So now what he's saying is, for these conditions, for Z naught equal 50 ohms, and the load equal to 150, he wants to know what the input impedance is for different line lengths. Now remember the formula, is it still up here? I'll put it down. The formula for Zn, if it's lossless, is a function of L, is Z naught times ZL plus J Z naught times the tangent of beta L, the attentive here, over Z naught plus J ZL times the tangent of beta L. And now he's going to give you some conditions. Before he does, I want you to write this down. You see how these tangent arguments have beta L in them? All right, beta is 2 pi over lambda. That's the wavelength on the line. Do you all follow me? Now, when I talk about A, it talks about line length being lambda over 8, is it?
Yeah.
He says the line length is only 1/8 of a wavelength. So that means beta L is what? Well, it's 2 pi over 8, or it's really pi over 4 And make a note of this, this is in radians, not degrees. It's very important you distinguish that. Pi over 4 radians is what, 45 degrees, isn't it? I would put your calculators in radians for this stuff. Just make sure you understand it. Do you follow me on this one, or not? Do you have a question? What is it?
Can you explain how you got it? That answer again?
All right, he says L is lambda over 8, right?
Right.
Beta is defined as 2 pi over lambda.
Oh, I see where you're, okay. I didn't see that lambda over 8.
Yeah, so that means if I have 2 pi over 8, right, the lambdas cancel automatically. I get pi over 4 radians. Now, what's the tangent of pi over 4 of 45 degrees? Opposite over adjacent is what? Think about tangent. It's opposite over adjacent. You're right, by the way.
Just one.
This is 1, this is 1. Opposite over adjacent is 1, correct?
Yeah.
Y'all agree with that? All right, so for this one, what happens to Zn? It equals Z naught, we'll put down Z naught, 1 plus J Z naught, right? Which happens, and then the tangent is 1, over Z naught plus J ZL, right? Now put down the values. Well, Z naught was, I guess I could divide. Let's see here. No, I'll just put them. So Z naught's 50, right? So I have 50. Oh, I'm sorry. This is, I messed up. This is ZL. My bad. Right there. So this is going to be 50 times ZL is 150, right? Plus J50, I should have divided, over Z naught is 50 plus J150, correct? Isn't that right? I want you to take a look at this. You see how the magnitude of this thing is going to be the same top and bottom? So the magnitude of the input impedance is going to be 50. It'll have a different phase. What happens? Let's see. Let's go ahead and divide. I'll leave the 50 on the front. Divide top and bottom by 50. We have 3 plus J1 over 1 plus J3. And if anybody has a complex or a calculator can do that for me, I'd appreciate it. Can't do that in my head. It's going to have a magnitude of 50 at some angle. So it's going to be 50 at some angle. And is his answer in terms of real and imaginary or magnitude and angle?
It's in terms of imaginary.
Real and imaginary?
Yeah, real imaginary.
All right, just tell me what this is in terms of real and imaginary.
So 3.5 minus 4.5, 3 over 5 minus 4 over 5 J.
Times 50, there's 50 up front, right? All right, so 3 over 5.
So 3 over 5 minus 4 over 5 J.
Times 50.
Yes, that's
Sorry. 3 over 5.
So 30 minus 4.
Times 4
Yeah, it's
over 5. J, so it's 30 times 50.
Yeah.
Right? So it's going to be 30 minus J40, right? Is that right?
Yeah, that's correct.
All right. So what's the next one?
It says do in terms of lambda over 4 as well. Or, yeah,
All right, so it says the length is lambda over 4. That's a quarter wavelength. This is an interesting one. I've got a comment about this in a second. So now I have a line length lambda over 4, right? The first thing you look at is going to be the value of beta L. So what is beta L for this one? Well, it's 2 pi over lambda times lambda over 4, right? And that's pi over 2, correct, class? Be attentive here. Now, what is the tangent of pi over 2?
Undefined.
It's going, tending towards infinity as you're approaching. Do you agree with that?
Yeah.
Here's what that means. This term dominates, and this term dominates. These two terms can be ignored. You all see that? All right? That's going to be so big that this term doesn't matter. This is going to be so big that this term doesn't matter. In the limiting case, you're going to get Z naught times Z naught over ZL. So that means for this one, right here, or B, Zn is just going to be Z0 squared over ZL. Z0 is 50, right, squared, and ZL is what? It's 150, right? So what's that going to be? Well, what is it? 2,500 over 150, 250 by 15, what's that?
Well, he's 2,500 over 50 is 50 over 3. And then,
Just 50 squared over 150 is what?
that would be 50 over 3.
Yeah, something like that. 16.7 ohms. Is that the answer?
Yeah, that's it.
Y'all follow me? It's really important about this. This is the one thing you got to remember. A quarter wave transformer is what this is. And the impedance going into this is always going to be the characteristic impedance squared divided by the load impedance. Now here's the nice thing about that. This only works at one frequency. Remember, beta is 2 pi over lambda, so it only doesn't work for many frequencies. But if I knew what the impedance was here, I want to match, I could design a length of line right here as a quarter wavelength and determine the characteristic impedance here to get exact matching, and that comes later. But just realize this is a thing you can do. It's called a quarter wave matching transformer. And another one on that one?
That for drill 228, that's just the only. See.
Okay, well, I'm going to mention one. That's not there. And here, I'm going to ask you this. So far we looked at lambda over 8. We looked at lambda over 4, right? Now pay attention. What happens if the length of the line is exactly half a wavelength? Well, if it's half a wavelength, then I'll do it over here. If all of a sudden the length is lambda over 2, what is beta L? 2 pi, right? Over lambda times lambda over 2 is pi, right? What's the tangent of pi? Tangent of 180 degrees is? 0. Y'all see that, class? That means the input impedance would be what? Well, these two go away. It's just ZL. Y'all see that? And this is one thing that's characteristic. It's always true with transmission lines. Every half wavelength, everything repeats itself. If you actually graph the voltage waveform, the magnitude of V of Z versus Z, every half wavelength, it would repeat itself. It's a very important property. So if I want the input impedance or anything else for a wavelength that is, say, 5.3 lambda long, I would just subtract the 5 lambda, because only the 0.3 matters. Do you understand that? That every half wavelength, the thing repeats itself. And we'll see more about that later. I'm just throwing that out there right now. And that's an important fact to keep in mind. All right, now, let me just see what's next, because we're not done with that. The complete circuit. Now we're getting into the complete, so we're going to have fun next. So we're going to use Dr. Whitworth's method. We're going to do this in the frequency domain. I always work in the phasor domain unless there's some overwhelming reason to do it in terms of differential equations in the time domain. It just doesn't make sense to make your life harder than it needs to be. So sometimes you have to. So now this is a complete circuit. What do I mean by that? I'll show you what I mean. So, start with a source voltage. You're going to have some voltage here, just Vs. It can be a magnitude and angle, but it's going to be the phasor domain. Then you're going to have an impedance here, some Z source. This is an impedance that has to do with the source itself. Are you all familiar that all your power supplies have some internal impedance? They're never zero impedance. I mean, they're close, but not, there's always something there. Now we're going to put the transmission line on here. And we're going to have a transmission line here with a characteristic impedance of Z0. We're going to assume this is a lossless line. And we'll put the impedance of the load here, ZL. And again, we're in the frequency domain. There's going to be a plus and minus VL here, voltage, and there'll be a current IL too that we'll talk about. And this transmission line is going to have an impedance, or I'm sorry, a length of L. Can you all follow me in this class? So I've just drawn what I've had before and I've added a source. Now, our goal here is to find this voltage and this current. So what we need to do is find the voltage there by finding the voltage here and then using the equations. And I'll show you what I mean by this. Now on this line here, this is going to be at Z equals 0. And this is going to be at Z equals minus L. So what we're going to do is this. We're going to find the voltage just at the beginning right here, and we'll call that V prime. That's the voltage just at the beginning of the transmission line. You with me on this, class? So here's how we do it. We first find the input impedance right here. So we find that impedance, and we know that what it is if it's lossless, Zn at L, the sum Z0, and it's times ZL plus J Z0 times tangent of beta L over Z0 plus J ZL times the tangent of beta L. So we're going to get that, and we're going to draw this circuit, where now we have our voltage Vs. Here's our input impedance, call it Zs. Then I'm going to replace all this with the input impedance right there. And this becomes Zn here. And what I want to do is get this voltage, plus to minus V prime. That's the voltage right at this point that is a superposition of the forward and reverse traveling waves at this point. You all follow me? So we're going to get it by simple voltage division. What is V prime going to be? Well, it's going to be Vs, right? And then it's going to be times Zn over Zn plus Zs. Can everybody follow me on that? That's simple voltage division, right? Take a good look, right? Now, I know at that point, right here, that has to be equal to the sum of the forward and reverse propagating voltages. Remember, anywhere on this transmission line, I have Vz equal to V0 plus times E, in this case, minus J beta Z plus reflection coefficient at the load times E to the plus J beta Z. Y'all follow me? That's the value of the voltage anywhere on the line. We can get gamma L just by knowing ZL and Z0, right? So I come over here and I say, well, that's equal to V0 plus, and it's going to be times E to the minus J beta. Now take a look at this. The value of Z here is minus L. Do you all see that? Real important you see this, correct, class? The value of Z at the input is minus L, because I made this 0. So this becomes minus J beta minus L or plus beta L. And then it's going to be plus the reflection equation at the load times E to the minus J beta L. I don't know what L is, I don't know what beta is yet, but obviously beta is 2 pi over lambda. You all with me? Now, I need V0 plus. Now watch this. So what do? I take this and I divide it into that. And I can say that V0 plus, which is going to be a scalar, is going to be Vs times Zn over Zn plus Zs. It's that, and it's got to be divided over 1 over E to the J beta L plus reflection coefficient of the load times e to the minus j beta L. I want you to, we're going to need this. This is real important. So we better start that one, restart. Now, once I have V0 plus, it's a lossless case. That's this, right? Take a moment, just write that down. I want to make this point. I'm almost out of time, but I'm going to get there. Now take a look at this for a second. You all see that when I'm at the load right there, to evaluate the load voltage, I just let Z equals 0. Can you all see that? When Z equals 0, I'm right here, right? That is Z equals 0. And that is the voltage at the load. So now I can say the voltage at the load right here, maybe I'll come over here because you've got the camera right there. I can say voltage, the load is going to be equal to all that, that right there, I'm just going to leave it V0 plus, because that's over there. And it's going to be 1 plus gamma L. Y'all see that? Gamma L is the reflection coefficient. And look, when Z is 0, it's just 1 plus gamma L times V0. There's V0, right? Y'all see that? So that is the voltage at the load. Got me on that one? Now, what about the current going in the load? What would that be? Just think back to circuits. If I got the voltage and I have the impedance, what's the current? Don't do that to me. It's not a trick question. What is it? It begins with an O, Ohm's law, right? What is it? Voltage over impedance, right? Y'all know that, guys. Why are you giving me a silent trick? Trying to help you. So it's just VL over ZL, right? I already got voltage and current. Ready for your bonus question? Let's see if you get a quiz on Monday. What was that? What? No, I'm kidding. How would you get the power at the load? Power dissipated at the load. What's fundamental? This is current voltage like you had before. Now I want the power, average power dissipated at the load. P-ab at the load. How do you get it? 1/2 the real part of what? V load times I load conjugated, right? All right, so there's V load. Right? I load is just that divided by ZL, but it's got to be conjugated, right? When you do all this, what's going to happen? You're just going to get the resistive part, aren't you? You want to know another trick to do this? Just do it this way. It's going to be 1/2 magnitude of IL squared times the resistance in the load, RL. So if the load had a real and imaginary component, you just take the resistive component. Because if it's got just reactive components, no power is lost. Average power dissipation is 0. Y'all follow me, class?
Yeah.
All right. Do I have more time?
No, this two. That's
2:30. I've got 2:32 now, but is there any questions? Okay, so I'm going to give you some homework. Please do it for Monday. I'm not going to give you these. That's a joke. The camera guy. But I do want to make sure you do the homework, keep up with this, because here's what happens. And this happens just about every semester like clockwork. People will wait till Thursday to do anything, and then they're dumbfounded. How? Why? They don't know what they're doing. Please keep up with this for all citizens. And if you really want to get a good grade, and I said this in an earlier class, don't just do the homework I assign. Do as many as possible. And I give you the solutions, Don. Didn't I give you the solutions, guys? Yeah. He knows, yeah. Do them all. I mean, you can't lose. It's only going to help you. Don't skip on this course. You will get flagged. I tell you, I hate seeing people flag this course. Please keep up. All right. I'm hanging around. Got questions for me?